So last section we talked about the binomial distribution, actually discrete probability distributions, and this section we're going to talk about binomial distributions. So a binomial distribution is a specific type of probability distribution. And in the last section of chapter 4 we'll talk about a geometric distribution, which is another specific type of discrete probability distributions. So what is a binomial distribution? Well, a binomial distribution comes up rather frequently. The type of problem comes up so frequently that it just has a special name. And the prefix bi typically means two, right? So basically you have two possible outcomes and in a binomial experiment is what we call it. And actually I should say binomial experiment. That's my bad. And basically there's four properties of a binomial experiment. So the first is the experiment is repeated for a fixed number of trials, so you'll know how many trials there are to begin with, and each trial is independent of the other trials. Number two, each trial is a success or a failure. Number three, the probability of success is the same for each trial. And number four, your random variable is counting the number of successes that you have. So to give you an example, let's say I flip a coin 3 times, so 3 coin flips, and I'm counting the number of heads. Well, in a binomial distribution, I could get 0 heads, 1 head, 2 head, or 3 heads. And these are my random variables, and this is a binomial experiment. Because each coin flip is independent from the other coin flips, the probability of getting heads is 1/2, and I'm telling you how many coin flips there are in the beginning. There's 3. So I want you to read some of these scenarios below and tell me if you think these are binomial or not. So hopefully you read these scenarios, and let's talk about them. So a certain surgical procedure has an 85% chance of success. A doctor performs the procedure on 8 patients. The random variable represents the number of successful surgeries. So this is binomial because you have a successful surgery or a failure. You have an 85% chance of success that doesn't change, and the number of trials is 8. And you're counting the number of successes. That fits all the criteria. Next one, a jar contains 5 red marbles, 9 blue, and 6 green. You randomly select 3 marbles from the jar without replacement. The random variable represents the number of red marbles. Well, the number of red marbles is what we're counting, so that's a success. However, this is not binomial because we're selecting marbles from the jar without replacement, and therefore the probability is changing. Okay. By the way, you still have 2 outcomes in this experiment. It's either red or not red. Even though there's 3 different colors, you can still put blue and green together as not red. So it doesn't violate the success or failure condition, but it does violate the probability changing. Because if I take a marble out and keep taking marbles out, and I'm doing this without replacement, the probability is changing. So that's the reason. So this is not binomial because probability changes. And then the last one is a multiple choice quiz that consists of 10 questions. Each question has 4 possible answers, only one of which is correct. To complete the quiz, you randomly guess the answer to each question. The random variable represents the number of correct answers. So this is also binomial. You have a success or a failure. You get the question right or wrong. Your probability of getting a success is 1/4, and you're counting the number of questions that you got right. So again, it fills all the criteria. Okay, so if you recognize that something is binomial, it's easier to figure out probabilities from that type of binomial experiment because there's a specific method we can use to find those probabilities. And before we get into that method, I'm going to show you how we get to that method. So basically, let's look at this problem. And this problem looks very similar to the problem on the previous page, except notice how we changed the words without to with. So a jar contains 5 red, 9 blue, and 6 green marbles. You randomly select 3 marbles from the jar with replacement, and a success is drawing a red marble. So if I'm selecting 3 marbles from the jar without replacement, that's how many trials we have. And if you looked at the previous page here, I gave you notation for binomial experiments, and this is something you should be familiar with. or should familiarize yourselves with now. So n, instead of sample size, is the number of times a trial is repeated. P is the probability of success. Q is the probability of failure. And x is the number of successes that we have. Remember, that's our random variable. So if I have 3 trials, or if n equals 3, well, if I pull out 3 marbles from a jar, I can get no red marbles, 1 red marble, 2 red marbles, or all of them could be red. So those are my 4 scenarios. Okay? My probability of success P is 5 over 20, or 1/4, right? Because there's 5 red marbles and there's 20 marbles total. If I add 5, 9, and 6, that's 20 marbles. So the probability of getting a red marble is 5 out of 20. My probability of failure has to be 1 minus P. So Q is always 1 minus P, which is 1 minus 1/4, which is 3/4. Okay, so P plus Q has to be 3/4. And if you identify N, P, and Q at the beginning when you recognize it's a binomial experiment, that does not change. So it's very important to identify N, P, and Q at the beginning. It'll help you out. And I always like to remember the phrase, mind your P's and Q's. Get it? Mind your P's and Q's. Okay. Anyway, fun math pun there. All right. So let's make a tree diagram for this scenario. Let's say we have a jar, we get a red marble, and R prime is not red. Okay, and we're doing this 3 times. So let's do it one more time. R, R prime, R, R prime. Do it one more time. Okay. And basically, each path on this tree diagram is one instance in the problem. So for example, I could have, every time there's a red marble, that's a 1/4 chance of taking that path, and every time there's a red R prime, that's a 3/4 chance. So I could write 1/4 and 3/4 on this whole for each branch where there's an R and R prime, but I'm not going to, because I think I'd run out of room and it'd get kind of messy. All right, so let's try to find the probability of no red marbles. Well, what path gives you no red marbles? Or paths? Well, if you think about it, there's only one, right? R prime, R prime, R prime. That's no red marbles, and that's the only way to get it. So if I want to find this probability, if you remember our tree diagrams, we multiply along the branches. So we take 3/4, another R prime is 3/4, and another R prime is 3/4, which is 27 over 64. So the probability of getting 3 marbles that are not red is 27 over 64. Let's do another one. What's the probability of getting 1 red marble? Well, this one's a little bit trickier because there's multiple ways to get 1 red marble. So pause the video here and see if you can find all the paths that get you 1 red marble. Exactly 1 red marble. So all the paths that get you exactly 1 red marble is R, R prime, this guy, R prime, R prime, this guy, or R prime, R. So all of those have exactly 1 red marble, but in all of those paths, what are you multiplying together? Well, in all of those paths, you're multiplying a 1/4 because there's 1 red marble and 2 3/4. But how many of those paths are there? Well, there was 3. So we take this and we multiply by 3. And the answer to exactly 1 red marble is also 27 over 64. I'll change my colors for this because it's going to get a little bit messier. What about 2 red marbles? Try to find all the paths again. Okay, so for 2 red marbles, that's R prime, R, and R prime, R. So these 3 paths. And once again, in all of these paths, there's 2 R's, there's 1 R prime, so we have a 1/4, a 1/4 for the R's, and then we have 1 R prime, and there's 3 of them, so we multiply by 3, and this one's 9 over 64. And then the last one is just 3 red, which is just the top path. That's 1/4 times itself 3 times. And we can double check our work here because remember, this is a probability distribution, so the sum of all of these probabilities should equal 1. And they do. If you add all of the probabilities together, you should get 1. Okay, so don't worry, you're not going to have to do this every time for every binomial experiment. But my point is that there's a pattern here that I want you to see. For example, if I want to find the probability of exactly one marble being red, we can look that up in our table, and that's 27 over 64. But if I want to find the probability of exactly one marble being red, what we're doing is we're finding how many ways can we get one red marble. Well, does it matter the order that we get the red marble? No, we just care that we have one red marble. And we learned from chapter 3 that there is something that counts the number of ways something happens when order doesn't matter. And you should remember that that is a combination. So out of the three marbles that we're taking from the jar, we're choosing one to be red. Then we take our probability of success, which is 1/4, and we raise it to the first power because we only have one red marble. And we take our probability of failure, which is 3/4, and we raise that to the second power because we have two not red marbles. And that's exactly what we're doing. If you look at the one red and two not reds, 3 choose 1. You could do that in your calculator, but you'll find that this is 3 times 1/4 and then 3/4 twice. And that's exactly what we did, which is 27 over 64. So this is basically a formula that you can use to find the probability of exactly one red marble, or basically it works generally for any binomial experiment. What about at least one red marble? Well, to get the probability of at least one red marble, you can get you can find the probability of one red marble, 2 red marbles, and 3 red marbles and add them all together. Or you could find the probability of, if we want to find the probability of at least one red marble, remember that's greater than or equal to. People always get these confused. Remember, greater than or equal to is at least, and less than or equal to is at most. So if I want to find the probability of at least one red marble, what I need to do is I can take the probability of no red marbles, because at least one red marble is 1 plus 2 plus 3, all these probabilities added together. But the complement is just the probability of no red marbles. So if I do 1 minus the probability of that x equals 0, I'm going to get the same answer. This is a very useful concept in binomial probabilities, and I can't stress this enough. Because if you understand the idea of the complement for binomials, you can save yourself a lot of work. So 1 minus probability of no red marbles. So out of the 3 marbles, we're choosing no red. The probability of success to the 0 power. The probability of failure. Well, if we have no red marbles, that means we have 3 failures. And this was 1 minus 27 over 64. Is when you evaluate it. That's what you get. And I think that gives you 37 over 64 as your answer. Okay, so let's apply this formula actually to a different example. And the formula we're using is right here. This is what it is generally written as. But I'll give you the formula, but like on a test or something. But I'd advise, if you understand how to use it and how it makes sense, it also makes doing the problems more easily. So let's go back to our first step, which is identifying N, P, and Q. We're going to read the problem. So read the problem and identify N, P, and Q first before you move on to the actual questions. So hopefully you paused the video and you identified N, P, and Q after you read the question. So it says a survey indicates that 41% of women in the United States consider reading their favorite leisure time activity. You randomly select 4 U.S. women and ask them if reading is their favorite leisure time activity. So N is the number of trials basically that we have. Well, we're asking 4 women, so our N is 4. Our probability of selecting a woman whose favorite leisure time activity is reading is 0.41. So I'm going to change that to a decimal because that's what we're going to end up putting in our calculator. And then Q is 0.59 because that's 1 minus 0.41. So that's how I got that. Remember, Q is 1 minus P. And we want to find the probability of exactly 2. So we want to find the probability that we get exactly 2 women of the 4 respond yes. So of the 4 women, we're choosing 2 to respond yes. For our probability of success, that's 0.41 to the second because we want 2 to respond yes. And if we have 2 successes, that means we have 2 failures, right? And that's exactly what our formula says up here. Let's see if I can get both on the same page, and I can. So this is the number of trials, which is 4. We chose 2. Our probability of success, P, is 0.41 to the how many successes, and then our probability of success, Q, 0.59 to what's left over. That's n minus x, which is 4 minus 2. So let's put this in your calculator. 4 choose 2, 0.41 to the second times 0.59 to the second, and you should be able to put this all on the same line. And when you do, after rounding to 4 decimal places, you should get 0.3511. Let's do the next one. The probability of that fewer than 2 respond yes. Well, the probability that fewer than 2 respond yes, you're going to have to do multiple of these, because if you're asking 4 women, you can have no women respond yes, all the way up to all 4 of them respond yes. Well, fewer than 2 is 0 or 1 women responding yes. So what you have to do is you have to find the probability of 0 and add the probability of 1. So you have to do the formula twice now. So out of 4 choose 0, we take 0.41 to the 0 because there's no successes, and 0.59 to the 4th, plus 4 choose 1, 0.41 to the 1st, 0.59 to the 3rd. And you can type this in your calculator and get an answer. Now, before you start typing this in your calculator, I want you to think about a couple things, because you don't have to type all of this in your calculator. For example, anything choose 0, if you have 4 objects and you're trying to find out how many ways you can select 0 objects, well, there's only one way to do it. You select 0 objects. That's it. There's only one way to select 0 objects, and that's to select 0 objects. So this is just 1. If you multiply by 1, it's not going to change your answer. So anything choose 0, you don't need to put in your calculator. Also, you should remember from algebra that anything to the 0 power is 1, so you don't need to put that in your calculator. So the only thing that really matters here is the 0.59 to the 4th. Also, some other things like the 0.41 to the 1st, we don't need to put to the 1st because anything 0.41 to the 1st is itself. And if you want to remember something a little bit extra, 4 choose 1, anything choose 1 is itself. So this is actually equal to 4. Because if you have 4 objects, how many ways can you select one of them? Well, there's only one way to select each object, so that's 4 ways total. So that's another thing you can remember. But even if you didn't remember that, I mean, just eliminating the 4 choose 0 into the 0 powers into the 1st power, I mean, that can save you a little bit of time. That's worth noting. Anyway, if you put these in your calculator, I suggest you do put them in your calculator just to verify you're putting them in your calculator correctly. You should get 0.4580. Okay, what about the probability that at least 2 of them respond yes? Now, at least 2, remember, think about it, is, what am I going to write in here? Greater than or equal to 2. Now, the probability of at least 2 is the probability of 2, 3, and 4 added together. So that means I have to do the formula 3 times. But you actually don't need to do the formula 3 times if you remember the complement. Because remember, the probability of all of these x values added together, if it's a probability distribution, equals 1. So if I just take 1 minus the probability that x is less than 2 and subtract that from 1, because that's these, and if I take, I'm going to use a different color here so you can see what I'm talking about. I'm trying to find the probability of what the blue bracket is, and I already know what the probability of the green bracket is. We did it in the previous problem. So I can just do 1 minus 0.4580, and that's 0.5420. And that's it. There's no formula needed. pretty simple. What about the probability that at least one responds yes? So this one, at least one responds yes. Once again, I could find the probability of 1 plus the probability of 2 plus the probability of 3 plus the probability of 4, or I could do 1 minus the probability that x equals 0, and then I only have to do the formula once. Because, once again, I'll rewrite my numbers here. You can find the probability of 1, 2, 3, 4 and add them all together, or you can find the probability of 0 and subtract that from 1. So if I just find the probability of 0, once again, then I can subtract that from 1, and I'll find the probability of 1 through 4. All right, so that would be 1 minus 4 choose 0, 0.41 to the 0, 0.59 to the 4th. 4 choose 0, gone. 0 to the 0 power, gone. So really it's just 1 minus 0.59 to the 4th. And 1 minus 0.59 to the 4th is... I had it here, but I lost it. Ah, 0.8788. Okay. Okay, so after you get the hang of this and using the formula, I don't think it's too bad. It just takes a little bit of practice and identifying what M, P, and Q is and stuff. So there's another problem on the next page, very similar to this one, but it's a binomial experiment. So try to find the probabilities on this on your own, and then I'll go over them with you like I did on this one. Okay, so hopefully you tried to do this page on your own first before I went through the solutions, because I think it's important to practice this on your own first. So first of all, you are taking a multiple choice quiz that consists of 5 questions, and each question has 4 possible answers, only one of which is correct. To complete the quiz, you randomly guess and answer each question. So your N is 5, your P is 1/4, your Q is 3/4. Because, and actually I'm going to make this 0.25 and 0.75 just because it's easier to put decimals in a calculator than it is to put fractions in your calculator. So depending on what you wanted to do, decimals or fractions, you may have one or the other. And remember, the probability of success is 1/4 because there's one correct answer out of the 4 choices. So we want to find the probability that exactly 3 answers are correct. So out of the 5, we're choosing 3. That's 0.25 to the 3rd. And that means that there's 2 that are incorrect. And that rounds to 0.0879. The next one is the probability of that at least 3 are correct. So this means that if you write it out, you get none correct or all 5 correct. At least 3 is 3, 4, or 5. So yes, you need to do the formula 3 times. There's really no way around it. So let's start with 3. 5 choose 3. 0.25 to the 3rd. 0.75 to the 2nd. 5 choose 4. 0.25 to the 4th. 0.75 to the 1st. And then finally 5 choose 1 or 5 choose 5. 0.25 to the 5th, 0.75 to the 0. And when you do all those, you get 0.1035. Okay? And you have to add them all together. And then the next one is probably that x is less than 3. Well, this is just the complement of the previous, so you just have to do 1 minus 0.1035, because if I want to find the probability that x is less than 3, that is just 0, 1, and 2 added together, but I already found 3, 4, and 5, so I can just do 1 minus the probability of 3, 4, and 5 added together, and that'll give me 0, 1, and 2 added together. So that's 0.8965. And then the last one, the probability that x is less than 5, is going to be 1 minus 5 choose 5, 0.25 to the 5th, 0.75 to the 0. again, anything to the 0 power is 1, and anything choose itself is also 1. Because if you have all 5 objects, how many ways can you select all 5 objects? There's only one way to do it. So really, you just need to do 1 minus 0.25 to the 5th in your calculator. And that's 0.9990, which makes sense, because if you're just guessing on 5 multiple choice questions, this is basically the probability of not getting a perfect score, which is going to be very high, because if you're just guessing, you're probably not going to get a perfect score. Okay, and that's basically using the binomial probability formula to find probabilities in a binomial experiment. Right? Now, I hate to make this video longer, but there's a couple more things that I want to talk about regarding a binomial experiment. So in a binomial experiment, there's also mean variance and standard deviation. Now, don't panic here, because this isn't really as hard as you might think it is. So if you recall, let's go back to the probability distribution of the marbles in the jar. So I'm just going to rewrite it here. This was 27 over 64, 27 over 64, 9 over 64, and 1 out of 64, I believe. And these were all the probabilities for finding a probability in a binomial experiment. And if you recall, to find the mean of a probability distribution, this is the formula. And to find the standard deviation, this is the formula. And these were pretty long formulas that we had to figure these things out. So I'm just going to show this just to show you what it looks like, okay, if you do this by hand. So if you want to skip ahead to show all the work, or if you want to watch me go through it, that's fine. But if you just want to skip ahead to show just to see the work of how I do this, that's fine, or you can skip ahead. It's up to you. Okay, so to find the mean, this is x times the probability of x, which is we have to multiply across. So that's 0 times 27 over 64, which is 0. 1 times 27 over 64. 2 times 9 over 64 is 18 over 64. 3 times 1 over 64 is 1 over 64. And if we add all these together, we get 48 over 64. So 48, 35, 45. 35, 45. This is 3 over 64. Yeah, you should get 48 over 64, which simplifies to 3/4. So our mean is 3/4. Okay, to find standard deviation, what you have to do, and I'm just going to do one column of this, so it's x minus mu quantity squared times the probability of x. So we have to take our x value 0, subtract the mean, which is 3/4, so that's negative 3/4, square it, that's 9/64. Okay, or 9/16, sorry. And then we have to multiply by the probability of x, which is 27 over 64. Okay, so the next one is 1/4 squared is 1/16 times that probability, which is also 27 over 64. The next one is 2 minus 3/4, so let's see, that's 5/4 squared is 25/16 times 27 over 64, or 9 over 64, excuse me. Okay, and then 3 minus 3/4 is going to be 9/81/16, I believe, and we're going to multiply that by 1 over 64. So now let's multiply all these. So let's see. If we multiply all these, that's 64, 128, 256, 5 to 1024, I believe, is our denominator. So this is going to be 81,243. This is 27 over 1024. This is going to be 225 over 1024. And this is 81 over 1024. Okay, and let me double check that I did this all correctly. So, gotta get my calculator here. So let's see, 243 plus 27 plus 225 plus 81, 576 over 1024. Yeah, then that's right. Okay. So if you add all these together, you end up getting, and after simplifying too, you end up getting 9/16. And the standard deviation, remember, is the square root of that, which is 3/4. So basically, you know, and maybe you just fast forward to the end, maybe you watch me struggle through that, whatever. But basically, it's a lot of work, right? Like this is a lot. This is a tedious task, especially for this probability distribution. It's not easy. Luckily for binomial formula, there's shortcuts. So on the following page, you can use the shortcut formulas for a binomial distribution. And for a binomial distribution, if you know NP and Q, you can find the mean, variance, and standard deviation. So the mean is n times p. And I'll just write down, remember we did 3 marbles. P is 1/4, Q is 3/4. So that's 3 times a fourth, which is 3/4. Go back to the work that I had, you'll see the mean was 3/4. The variance was NPQ, or is NPQ, which is 3 times 1/4 times 3/4. Go back to the work, you'll see 9/16. And then the standard deviation is the square root of NPQ, which is the square root of 9/16, which is 3/4. So these formulas are so much easier to use to find the mean, variance, and standard deviations. But the key is, this is only binomial. It does not work every time. It's only if you have a binomial experiment, which is why it's nice if you recognize that you have a binomial experiment, because then you can use these simpler formulas. And of course, you have to know the formulas. But these formulas are available to you on your formula sheet. You just have to know when to utilize them. Okay, and that's basically a binomial experiment. Next, we'll talk about a geometric experiment in section 4.3, and don't worry, it's not as long as this video.